Turn on the recording and let me share my screen. All right, so Assalamu alaikum. Today we're going to talk about semiconductors, which is one particular application of the kinds of concepts that we've learned so far in the Condensed Matter Physics course. And as you can well imagine that this is a topic which has revolutionized human civilization. So it's really physics, quantum physics and band theory, which is at the heart of the discipline of semiconductors. And we all know that we now exist in a sense because of semiconductors. Our lifestyles, the way we work, the way we think, the way we interact with one another is due to semiconductors, which are at the heart of the entire digital revolution, the entire electronics revolution. So physics is, in a sense, of civilizational essence. It really has an imprint on our lives, which is inescapable. So today, however, we're going to look at a very mundane and a very low-level view of semiconductors, and we'll just look at the basics of how these materials are formed and what kind of underlying concepts do they harbor, and we'll draw upon the strengths of the band theory that we've been discussing so far in elaborate detail inside this course. All right, so can you hear me well? Is my voice audible?
Yes, sir. ठीक है.
All right, okay. All right, so semiconductors are kinds of insulators in which the band gap between two bands is small, and those bands are the valence band and the conduction band. So the distinction between semiconductors and insulators is more of a choice, or is a matter of opinion. We know that if we have a band structure, a lower band and an upper band, and if the lower band is completely filled, then there is no place for the electrons to go to. They must cross a barrier, which we call the band gap, if they would like to make a transition to empty states. That's the nearest location where filled electrons can find empty states. So depending upon the size of this band gap, we can classify materials as insulators or semiconductors. Something that is around the order of 1 to 2 electron volts is generally called a semiconductor. And if it's larger than that, 4 electron volt, 5 electron volt, we classify such materials as insulators. And a material which is a semiconductor in certain regimes can turn into an insulator in other regimes. So it's a matter of opinion and a matter of taste. However, semiconductors have special properties, and they come up with their own variety of characteristic and unique properties which make them so special. And that's what we're going to discuss today. So first of all, let me draw two bands. Here they are. So when I draw bands of this kind, generally the x-axis is some momentum k, and the vertical axis is some energy. The lower band is generally called the valence band, VB, and the upper band could be called the conduction band, CB. And what I've drawn in front of you is a direct band gap semiconductor. It's direct because the maximum energy in the valence band coincides with the minimum in the energy of the conduction band. So the band extrema, they overlap in K space. So this is an example of a direct band gap semiconductor. The difference between these two extrema, let's call it the band gap EG. Now I've drawn these bands in a special function, and I've drawn them in a way so as to highlight the difference in curvature between the bands. And the curvature is defined as the double derivative of the energies of with respect to the K space. Now, what are these energies? These are energies of the electrons, right? And there are going to be levels inside the valence band and levels inside the conduction band. That's what an energy band really is. Now, suppose we are at 0 Kelvin. So there is no thermal excitation, which means that the electrons are frozen into their ground energy states. What's going to happen is that this valence band is going to be completely filled, and the conduction band is going to be completely empty. So this material is going to behave as an insulator at 0 Kelvin, and no thermal energy is available because the material is at 0 Kelvin, so as to promote the electrons from the valence band to the conduction band. All right. So here these energies, this E that I'm talking about is the energy of an electron. All right. Now you will notice that in the valence band and the conduction band, the curvatures are totally different. So if I focus my attention on the conduction band for the time being, I can find out what the energy of the electron is. Let's focus our attention first on the conduction band. So here is my conduction band, and this is the point K where the energy of any electron, if it were to exist in the conduction band, would be the minimum. All right. So suppose an electron comes into the valence conduction band somehow. It has been promoted by external illumination, photoexcitation, or some process. So an electron that was initially in the conduction valence band has been promoted by some process of thermal or optical excitation, and it has now gone into the conduction band. Now this electron will have some energy, and the energy of the electron will depend where the electron is in the K space. All right. So the energy is going to be a function of K. And if we are close to the minimum of the band, that is, we are close to K minimum, we can express the energy as a parabola. So if we do a Taylor expansion of the energy about the K minimum point, we can write this energy as some minimum energy, which is this energy here, E minimum, plus some constant alpha, and the deviation of K from the K minimum squared. Since it's a symmetric band, we don't have a linear term, we only have a quadratic term. Of course, there will be higher order terms as well, but if we are close to the bottom of the band, we are justified in keeping only the lowest order term. So this is the energy of an electron in a conduction band close to the trough of the band, the lower part of the band. And if I focus my attention for the time being just on one dimension for simplicity, this is going to be alpha K minus K minimum squared, plus higher order terms, which for the time being I'm ignoring. Now, we all know that if we were to define an effective mass for the electrons, that effective mass is going to be given by h bar square over partial square E over partial k square taken at the minimum. And if we look at this energy dispersion relationship, find out the double derivative, we'll be left with an expression that uh, ME is, okay, let's find what this thing is going to be. So the first derivative is 2 alpha k minus k minimum, and the second derivative is going to be equal to 2 alpha. All right. So in other words, h bar square over me star is going to be equal to 2 alpha. So the effective mass of the electrons inside the conduction band is going to depend upon this constant here. All right. So bands with a different curvature will lead to different effective masses for the electrons inside the conduction band. So one is the bare mass of an electron, a free electron. In a conduction band, the effective mass can be different, and it depends upon the curvature of the bands. So this is how we can define an effective mass of an electron. Now, equally important is the concept of a hole. When an electron is promoted to the conduction band, it leaves in its wake a hole inside the valence band. So this object here acts like another particle with a positive charge, because it's the absence of an electron. An electron has been taken away from an otherwise neutral band. This band on its whole is charge neutral. There are as many, uh, it's a piece of solid, it's uncharged. The positive ionic cores balance out the negative charges of all the electrons, so it's a perfectly charged neutral band. And if you take an electron outside from this band, it leaves in its wake a positively charged object or a particle, which is called a hole. All right. So the hole is generally represented by an empty circle, and I can represent an electron by a filled circle. And this excitation between an electron and a hole is just similar to the pair production process, in which an electron and a positron can be created from vacuum. Okay. Likewise, the electron can fall into the hole and be annihilated. So the electron and the hole can also annihilate one another. In semiconductor physics, this is called recombination. So we can create charge carriers, we can generate charge carriers, and we can also recombine them. All right. So an electron and a hole can recombine. They can annihilate one another to give you vacuum or nothing. And an electron and a hole can also be regenerated from nothing. So you can separate out the charges or keep them lumped together to form a neutral entity. All right. So as electrons, holes live inside the production band, inside the valence band, and they also carry energies. So if you look at this conduction band, we can also define an effective mass for the holes. And the effective mass for the holes is defined in an absolutely analogous fashion: h bar square mh star. Mh is the effective mass of the hole, and this equals also this equals to alpha, where alpha is taken to be positive, and this energy dispersion relationship, by the way, is given by E k is some E max, which is this energy E max minus alpha k. This point here is now k max minus k max modulus square. All right. So one could take the double derivative again, and one can arrive at this expression. So we can have effective masses of electrons and effective masses of holes. Generally, in normal semiconductors, these effective masses could be smaller than the mass of an electron. They could be half the mass of an electron. They could be one third the mass of an electron, one fifth the mass of an electron, and so on. So the band curvature defines the effective mass. All right. Now, the key point that I would like to emphasize here is the band structure was drawn with reference to the electrons. So the band structures arose because the electrons were being treated as waves, and these waves live inside a periodic potential. And inside the periodic potential, we saw that at the zone boundaries, gaps appeared, and so on. Now, the important the important point is that the holes also have a certain energy, and the direction in which the energy increases for the holes is going to be different from the electrons. Now, let me explain this concept. Suppose I have this valence band and a conduction band, and I draw two scenarios. One scenario is that an electron is promoted from the top of the valence band, goes to the conduction band, and it leaves a hole in its wake. Sorry. One hole is left here. Now let me draw another scenario in which an electron is promoted from this point in the K space, and it might go somewhere here. So even though this might be a slightly difficult process, but just for the sake of argument, consider that the electron in the right case has gone from lower down inside the valence band and gone to the conduction band. Now, as far as the electron is concerned, the electron in the case that I've drawn on the right, in order for this process to occur, the electron has gone from lower down into the energy, lower down in the energy, and crossed the band gap. All right. So the energy in the system has gone up overall. This means that this hole here, if you compare the hole on the right to the hole on the left, this absence of an electron carries more energy than the scenario on the left. Taking out an electron from lower down inside the conduction band is going to cost more energy. Therefore, a hole that is lower down in the conduction band will have a higher energy, whereas an electron that is higher up in the conduction band will have a higher energy. So let me write this down. An electron higher up in the conduction band is a more energetic electron. And if I were to take a hole from the, say, the top of the valence band, I take a hole here and move it down in the valence band, it means that the energy of the hole is going up because I'm shifting an electron upwards in energy. Therefore, when the electron is shifted upward in energy, it creates a correspondingly a hole with a correspondingly higher energy. So holes go higher energy if they are lower in the valence band. So sometimes this is represented by noting down that the energy of, if I were to take an electron from a K point, an electron that lives inside a K point, at a K point, its energy is the negative of the energy of a hole at the same K point. All right. So for electrons in in the conduction band, an electron that is higher up in the energy means that its energy is going up. Whereas for holes, the energy goes up if the hole is lower down in the valence band. So this is the energy for the holes, and this is the energy for the electrons. So this is just like if you have a pool of water, and the analogy some authors use is put a balloon inside the pool of water. Lowering the balloon inside the pool of water is going to cost energy. So if a hole is to move inside the valence band, its energy goes up when it goes down inside the band, because that means when an electron goes down inside the valence band, it means that the electron has been taken out from lower down, deeper down inside the valence band, has been promoted to the conduction band. So that costs more energy. So the holes going lower down is really tantamount, is really equivalent to saying that electrons have been promoted from from the lower trenches in energy inside the valence band. So the overall energy of the system has to go up. Any vacancy of an electron created, which is given the name of a hole, deeper down inside the valence band will have a higher energy. All right. So this is what this is something that is really worthwhile to understand. So any questions about this? By the way,
पे जो ये इक्वेशन है, ये अभी एग्जैक्टली जो अभी ये डायग्राम्स के ऊपर ई के इक्वेशन ऊपर, ये जो आपने दो डायग्राम्स बनाई थी कंपैरिजन के लिए यहाँ पर, तो यहाँ पर माइनस अल्फा
alpha square, alpha.
बोलो
So the convention that, so people are not consistent in defining whether the effective mass of a hole is positive or negative. I'm taking this to be positive. All right. So by the way, in the close to the maximum or minimum of a band, the band can be approximated by a parabola, and that can be done for any function that close to its extremal point. All right. Now, the important point is that we can define an effective mass near these band maxima and minima. And there was a homework problem in which dealt with the tight binding model, in which we found out that the effective mass was proportional to 1 over the hopping parameter t. So all bands can be represented in the vicinity of these extremal points by a parabola. All right. And we can always write down energies as h bar square sum k, so minimum or maximum modulus square over 2m star, where m star is the effective mass. So this is the, so you can assume near the band extrema that the particle is almost free but with a modified effective mass. Okay. So this, if you compare this expression with this expression, or with this expression, you can determine what this m star is going to look like. It's going to be inversely proportional to this term alpha here. Okay. So the effective masses depend upon the curvatures. All right. And you can have heavy holes and light holes depending upon the curvature of these electronic or hole energy bands. All right. So now I would like to talk about semiconductors in some more detail. But before I'm able to do that, I'm going to give a lightning fast introduction to the Drude model for electrons. Now, we know that the free electrons inside a metal, they are not really free in the sense they have to obey the Pauli exclusion principle, and there is a particular limit that each quantum state can only be occupied by electrons of a single kind if we include spin. So each k level can be occupied by two electrons, but they have to have opposite spin. So the Pauli exclusion principle raises the Fermi energy and it raises the degeneracy pressure. However, if the electrons are far and few and many energy levels are available, then such a gas of electrons can be treated as a real gas, as an ideal gas of electrons. And this is the classical free electron theory. And you must have studied this in modern physics, and we have also hinted at it in this particular course. So in semiconductors, if you have charge carriers which are sparse, which are very far and few, and a large number of energy levels are available, which means that the whole band is available for these electrons to occupy, then such electrons uh, can be modeled through the kinetic free theory of gases. And this is what the Drude model really is. So in a Drude model, an electron inside the conduction band or a hole inside the valence band, both of them, by the way, contribute to conductivity. They can be modeled as a classical billiard ball collection of particles as a true ideal gas. And then you can write down the Newton's laws of motion, the equations of motion for these particles. For example, if we were to take uh, the Newton's motion for electrons, you will have to take, however, the effective mass of an electron inside the conduction band. You can define a velocity or the group velocity for electrons. And this is the force on an electron. And this is going to be given by the charge on an electron, which is minus E, the electric field, plus velocity into the magnetic field, right? So this is the basic equation, the equation of motion of an electron. The only thing is that you have to take into consideration now the effective mass of the electrons. So that's the utility of the concept of effective mass. It's not the bare mass, it's what the mass that the electrons see inside the band, and that is the effective mass. And if we were to include scattering between electrons, an electron can collide with ions inside the metal, then you'll have to include a damping factor in this equation. And the phenomenological or the empirical damping factor that is included is generally given in this form: minus me star v over some scattering time tau, where tau is the mean time required for the mean free path of the electrons. That is the average time of collisions between an electron and an ionic core. So you can imagine that this term here is like an electronic viscosity. And if we talk about the circuit model, this is like a resistance for the charge carriers. All right. So likewise, we can also write an equation of motion for the holes. The holes, of course, have a positive charge. All right. All right. So what is this V here? Now we've defined the effective mass in terms of the band structure. We should also be able to describe this velocity, which is sometimes called the drift velocity of these charge carriers in terms of the band structure. Now, if you look at free electrons, the energy of free electrons is h bar square k square over 2m. So this is, we already know this. So if I were to take the derivative of this energy with respect to k, I'll get h bar square k over m. All right, and I can write this as h bar k over m. And this h bar k, according to the de Broglie relationship, is simply the momentum of the electron. And the momentum divided by the mass of the electron is speed. All right. Sometimes this is called the group velocity. So if I were to take the group velocity of free electrons, this is going to be given by the derivative of the slope of the bands, the derivative of the electronic energies with respect to k divided by h bar. Now, if you were to extend this concept to 3 dimensions, and we're not talking about electrons here, but general charge carriers inside valence or conduction bands, they could be holes, they could be electrons, then we can define a corresponding velocity, excuse me, a vector as 1 over h bar. Now, instead of this single unilateral gradient, we have a proper gradient, which is represented by the del operator acting on the electronic energies. And there's a subscript k as well, which says that we are differentiating inside the k space. So this is our definition for the group velocity. And you can find out what the you can really find out what the velocity for the electrons and the holes can be, and it comes out from the electronic and the electronic band structure. All right. So it turns out that if I were to take the group velocity for the electrons at a certain point in k space, this is absolutely equal to the group velocity for the holes that exist at that some k space. So if an electron is at a k point, it might have a certain group velocity. And if I take the electron away from that k point, a hole is formed at that k point. That hole will have a group velocity exactly equal to the group velocity if that point, k point, were occupied by an electron. And this is evident from this relationship that we have over here. So this k could be for an electron. If this is for an electron, this is the energy for an electron. So we've seen that if we were to consider holes, the energy for the holes is the negative for the energy for the electrons. But the momentum vector for a hole is also negative for with respect to an electron. So if I have an electron with k vector k, its momentum is going to h bar k. And if I take that electron away, then the momentum is going to reduce by h bar k at that point. So I can say that a hole is created with an opposite momentum minus h bar k. So if I were to consider electrons, I'll have a relationship del k e for the electron. This is exactly equal to minus k, the derivative with respect to minus k for e for a hole, because this is the negative of the electron. This energy is the negative for the electron. So these two expressions are totally equal as far as the hole and the electron is concerned. So the group velocity for the electrons and the corresponding holes are going to be equal to one another. And we're going to look at several examples of this. So you'll have to be patient with me on this count. All right. So now let's move on to some real semiconductors. Any questions up till here?
सर ये आपने इसको जनरलाइज करके डेल ऑपरेटर्स का कैसे लिखा था ग्रुप वेलोसिटी को, वो दोबारा बता सकते हैं? ये जो आपने स्क्वायर में लिखी हुई इक्वेशन, इससे ऊपर वाली इक्वेशन से ये वाली इक्वेशन कैसे आई थी?
All right. So if I have Vj E1 over h bar, this is in one dimensions. All right. But this is really a vector. It will have an x component, a y component, and a z component. So what I really want is I need to define an x component is going to be epsilon. This is in an x direction. Let's call it I. Now these are directions inside the real space plus all right. So this is the group velocity in vectorial form. All of this in shorthand can be written as the gradient operator acting on the energy bands with respect to k. All right, Bilal?
यस सर ठीक है, बस 3D में था वो, मुझे बस कंफ्यूजन हो रही थी। ठीक है, ऑलराइट।
All right. So now we are all very well aware of what intrinsic semiconductors are. Intrinsic semiconductors, for example, silicon, germanium. Now, each silicon atom has 4 valence electrons. So it binds together tetrahedrally with 4 neighboring silicon atoms. We know that it has an FCC structure. It belongs to the space group FD3 bar M. We've seen that in detail in the previous lectures. And all those 4 electrons form covalent bonds with neighboring silicon atoms. All right, so everything is so far so good. So I can draw this network in a cartoonic fashion in 2 dimensions by the silicon atoms. And they are forming these bonds with neighboring silicon atoms. And it's tetrahedrally bound to 4 neighboring atoms. So the coordination number is 4. And there are 4 electrons inside the valence. And this is how these electrons pair up and form covalent bonds. Now, if I were to ignore the curvature for the electrons at the moment, now I'm going to draw energy bands as is normally done by semiconductor physicists. They forget about the curvature for the time being, and they just draw these straight bands, a valence band and a conduction band. And if you're at 0 kelvins, there are electrons inside the valence band, and the conduction band is totally empty. These electrons are not free. They cannot contribute to conductivity. All right. So I forgot one thing in the Drude model. Let me uh, back up a little bit here. If I look at these equations, so for example, if I look at this equation, I can find out the mobility, I can find out the conductivity, and so on. For example, so I'll come back to the semiconductor. So, but let me finish the argument for the Drude model. I just forgot it. So if I have ME star dV by dt is minus E VE. Suppose my electric field, my magnetic field is 0, minus ME star V over tau. Now, if I'm in a state of equilibrium, I've applied an electric field to my free electrons, to my Drude electrons or my Drude holes, then this term is going to be zero because there is no force acting. Then that means that my EE, if I were to talk about magnitudes only, is going to be ME star V over tau. All right. So I can just do a bit of manipulation, E tau over ME star E. So if you look at this expression over here, we can talk about in semiconductor physics of the concept of mobility of charge carriers. The mobility of charge carriers is a constant of proportionality that relates the velocity of charge carriers to the electric field. So higher the electric fields, what is the resulting equilibrium velocity for charge carriers? All right, we all know that you apply an electric field to a charge carrier. We've seen that when we were talking about the effective mass. You apply an electric field, a force acts on the charge carrier, the force accelerates the electrons, but the electrons are experiencing some scattering by collisions. So an equilibrium velocity is reached, and we would like to find out how big is that velocity in response to electric field. So we can define a relationship between the velocity and the electric field that is controlled by this constant proportionality, which is called the mobility, which could be different in different directions. It could be anisotropic, but let's neglect that for a minute. So if we look at the mobility of charge carriers, we can have a mobility, for the electrons, which is given by E tau over ME star. Likewise, we can have a mobility for the holes. Each one of them is dependent on their effective masses, right? And this scattering time goes up, which really means that the mobility goes up. So longer scattering times means further and fewer collisions and scattering events for these electrons or holes. Longer, higher will be the mobility. All right. And by the way, so in addition to mobility, we can also define a conductivity. And the conductivity is given by this expression, which relates the current density in these electrons. So in response to electric field, a current can flow through these materials. And the constant of proportionality between the current density and the electric field is called the mobility. And from basic modern physics, you already know that this conduction or electricity magnetism, you already know that this current density is given by the charge carrier concentration into charge into the drift velocity. All right, so it's evident that from here that if I were to place this V in here, V equals this E tau over M, I get E squared tau over ME. Suppose I'm talking about electrons. Okay, so the conductivity can also be expressed in terms of the scattering parameter and the effective mass. And by the way, if I have both electrons and holes inside the system, as we have in intrinsic and extrinsic semiconductors, as I'll show in a minute, we'll have conductivity due to both the electrons as well as the holes. The electrons are moving inside the conduction band and the holes are moving inside the valence band. All right. So the conductivity overall is n times the concentration of the electrons. And when I say electrons, now when I say electrons in semiconductor theory in the module, I mean free electrons, electrons that live inside the conduction band. Okay, mostly the majority charge carriers. E square, the scattering time for the electrons divided by ME plus the charge carrier density for the holes, E square, tau for the holes, MH star. All right, so both the electrons and the holes can contribute to the current. And since they have different k vectors, you already know that they have opposite k vectors. If in response to an electric field, if an electron moves to the right, the hole would move to the left because they have opposite charges as well. So everything just gels in. The opposite k vector concept also gels in nicely with the physical interpretation. All right. So now let me come back to the intrinsic semiconductors example that I've already started. So this is the energy band diagram that's in front of you. And by the way, I've suppressed the curvature of the band just for simplicity, as is normally done. This is the band gap, EG. Now, if some process occurs of excitation, these electrons that are living inside the valence band, they cannot conduct electricity. So some kind of excitation happens. A light beam comes in of a certain frequency, which is correctly tuned at the band gap, or the temperature goes up. So the thermal energy goes up. These electrons are going to be promoted to the valence band and they're going to produce holes. And by the way, in an intrinsic semiconductor, there are no impurities. So all of them are just silicon atoms. Silicon is the purest known or engineered material for mankind. You can nothing purer than silicon or these semiconductors or germanium or gallium arsenide has ever been made. All right, so these are the purest materials known to man. So when we engineer these materials and there are no impurities whatsoever, no dopants, then the number of holes is always going to be equal to the number of electrons, the number of free charge carriers, because an electron and a hole is always created in tandem. They're always created as a pair through a charge carrier generation process. All right. So if we were to draw the band gap diagram for an intrinsic semiconductor, we can have electrons, we have holes, the same number. So in an intrinsic, Ni, which is the number of electrons in an intrinsic, this I stands for intrinsic, is the same as Pi, where P represents the number, the concentration of holes inside the intrinsic. This is how we define an intrinsic semiconductor. All right. Now, what if we higher the temperature? So you can increase the temperature, the number of holes will go up. Later, we will show that uh, this that these we will find explicit expressions for the number of charge carriers. All right, it depends upon the temperature and it depends upon the band gap. All right, so we'll derive the exact expression for how many holes per unit volume exist for an intrinsic and how many electrons per unit volume exist for an intrinsic semiconductor. Now, what if in this network of silicon atoms, this nice network of silicon atoms, all of a sudden we introduce a say a nitrogen atom, or a phosphorus atom. Now, everywhere we have these nice bonds between the silicon atoms, tetrahedral covalent bonds. All the electrons are nicely paired up. Nice covalent sigma bonds are being formed. But this nitrogen has it's a pentavalent atom. It belongs to group 5, so it has 5 electrons. So it has an extra electron somewhere, all right? So now inside this host matrix of silicon atoms, we have introduced nitrogen atom, a pentavalent impurity. Okay. Now, this is called an N-type impurity. And what four electrons are participating in coordination? They are participating in the formation of the valence bonds, covalent bonds. And the fifth electron acts belongs to the ionic core. The ionic core is the nitrogen nucleus, 7 protons, 4 electrons. uh, Nitrogen has 7 electrons in total, 2 electrons in the first shell, 5 electrons in the second shell. So 6 of these electrons are a part of the either the ionic core or the covalent bond. The seventh electron has the potential to become free. So we can view this nitrogen plus the seventh electron as a kind of hydrogen atom. All right. The hydrogen atom is an electron and an ionic core, which in that case is just a nucleus. So now we have like what is generally called a Rydberg kind of atom. The Rydberg atom, you have a single electron in the valence shell, very far off from the nucleus, and an ionic core. And you can find out the energy levels for such a system. You can find out the Bohr's radius for such an atom, exactly as we do for a hydrogen atom. We know that for the hydrogen atom, the energies are quantized according to quantum number n, and they're given by a Rydberg constant square. I'm just talking about the bare energies. This is about 13.6 electron volts. So the ground state electron is 13.6 electron volts below vacuum. So if you have vacuum, which is the ionization state, in which the electron becomes free, vacuum means free electrons. The n equals 1 state for hydrogen is 13.6 electron volts further down. Now this constant Rydberg, so I've noted it down, is given by, you all know this is me square epsilon naught square h square. Now if you were to talk about an electron, a Rydberg atom, nitrogen atom inside the silicon matrix, you'll have to do two modifications. The first modification that you would require is, now I'm talking about the Rydberg constant for this impurity, for this n-type impurity. You have to replace this m with the effective mass of an electron, charge of an electron 8, and instead of epsilon naught, we'll have epsilon naught square relative permittivity square. So 8 square. So this really means that the Rydberg constant for the n-type, if I take its ratio with the Rydberg constant for the hydrogen atom, this is going to be m e star over m e and 1 over epsilon r square. This is the ratio. Now silicon or any semiconductor material has a particular permittivity constant, dielectric constant, generally of the order of 10 or 11. Silicon, it's 11-ish. And me star is also smaller than me. So overall, the energy levels, the ground state energy levels is shrunk by perhaps an order of magnitude. Okay. And if you were to perform this calculation, this would turn out to be around, say, 0.1 electron volt, roughly. So now the ground state for this electron is a paltry 0.1 electron volt below the vacuum level. All right. And it can be easily ionized. It can easily be promoted to the conduction band, in other words. So if I were to intentionally introduce a dopant atom, an N dopant atom, nitrogen atoms or phosphorus atoms into my pure matrix of silicon. And this does not happen this in this fashion, by the way. It happens more carefully in an engineered fashion. It's a bottom up approach generally. You don't bombard nitrogen atoms onto the silicon. You grow them in a very nice, pristine fashion. But whatever the case is, if we introduce these impurity atoms, and still they are sparse, say a million silicon atoms and one phosphorus, one nitrogen, that's it. That's the ratio that is commonplace in N-type semiconductors. Then the energy level diagram is going to be modified. And how is it going to be modified? It's going to be modified in this fashion. So this is my valence band, the conduction band. Now I have an additional level of electrons below the conduction band, slightly below the conduction band. So this is could be 0.1 electron. All right. And if I were to look at the energy, the occupation of the electron, so at 0 Kelvin, the electron will be in the valence band with no holes, no electrons really, because there's not in the valence band. But these energy levels are going to be occupied by electrons. And how many levels are formed, or how many electrons do we have here? As many as there are the donor atoms, because each donor atom is giving one electron. So you can imagine that on this uh, axis, I'm plotting distance as I go into the material. And here I have energy, of course. So this new level that is created inside the gap. Now a level is created inside the gap. This is called a donor impurity level, or a donor level. In fact, a small band of electrons because of the scattering and other effects and other impurities. A small band is formed just below the bottom of the conduction band. Okay. And this is called a donor impurity level. And electrons now reside inside this level. And if you give them a slight nudge of energy, so this is 0.1 electron volt, by the way. So thermal energies are 25 of the order of 25 milli electron volts. So if you give a slight uh, nudge of energy, a very slight nudge of energy, these electrons can really be promoted into the conduction band very easily. All right. So you can get electrons inside the conduction band by two processes, either by the thermal generation of electrons that is coming right from the valence band, or you could get electrons, a much higher fraction of them, from the slightly low level lying donor impurity states. These electrons are readily available because the gap between the conduction band and these donor levels is very small. A slight thermal energy can excite and promote these electrons. All right. Likewise, if you have a p-type impurity like boron, which has 3 electrons, we are going to form acceptor levels slightly above the valence band. All right. And if a slight amount of energy is available, this can create the formation of holes inside the valence band. Remember that going lower down for holes is going to increase this energy. So if a slight amount of energy is available, the holes, you can imagine that the holes that are lying on this acceptor impurity level, they will be promoted to the valence band. And these holes will now become charge carriers inside the valence band. All right. Now, so these are what are called extrinsic semiconductors. In extrinsic semiconductors, N is not the same as P. The number charge carrier density for the electrons is not the same as that for the holes. There is either a preponderance of electrons or a preponderance of holes. Preponderance means a majority. All right. So for an N-type semiconductor, the electrons are the majority charge carriers. They will still be holes because, of course, there are going to be thermal generation of charge carriers, but the holes will be minority charge carriers. For a P-type semiconductor, the holes will be the majority charge carriers and the electrons will be the minority charge carriers. All right. So in a sense, a new energy level is created here, which is called, could be called ED, the donor energy level, and a new energy level is created in the P-type semiconductor, which can be called an acceptor level impurity level EA. And these energy levels are found inside the band gap. Very interesting. So readily available charge carriers right next to the conduction band or the valence band. And it of course also modifies the optical properties as well. Now, instead of making a transition all the way, all across the band gap, a slight transition is needed in the valence band, in the end type, the gap that needs to be overcome is now, if I call this EC, the bottom of the conduction band, and I call this EV, the top of the valence band. So the band that now has to be crossed inside the band gap that has to be surpassed in the case of the N type is now EC minus EV minus ED. And here the band that has to be crossed is V minus EA or EA minus EV because EA is higher. All right. Now, any questions up to this point? So remember that if the in these intrinsic semiconductors, we generally talk about three regimes of temperature. One regime is called the ionization regime. Then we can have the extrinsic regime. Then we can have an intrinsic regime. No matter what kind of semiconductor we're talking about, we can identify three distinct regimes. In the ionization regime or the carrier freeze out regime, what happens is that the temperature is so low, it's so low that this transition from, let me change colors, this transition from the donor impurity level to the conduction band is not possible because EC minus ED is much larger than the thermal energy. If this is the case, then no charge carriers will be present. So this is like a freeze out of carriers. Okay. So this is called the ionization of the carrier freeze out regime. In the intrinsic regime, which goes where EC minus ED is slightly above, it is above KBT, then charges can be promoted from the impurity level to the conduction band. But these charges are coming from the dopants. The energy is still not large enough to make this possible. So most of the conduction is taking place due to charge carriers that have been promoted by the donor atoms. So in the extrinsic regime, if I talk about N-type semiconductors, the N is almost due to the donor donated electrons. All right. So this is the regime in which you would like to make an extrinsic semiconductor work, and you would like to exploit the properties of an extrinsic semiconductor or a doped semiconductor. But if the temperature goes really large, it's possible that this this transition becomes possible, which means that EC minus EV, the temperature is so large that it overcomes this band gap as well. In this regime, the intrinsic regime sets in, and the majority carriers, the minority charge carriers, the electrons and the holes also start contributing to the conduction, because now electrons and holes can be easily formed. A promotion from the valence band to the conduction band takes place. All right. So in this regime, N could be Nd plus Ni. And if the temperature is really large, it could primarily be due to only the intrinsic electrons. So these are three regimes for a semiconductor, and we'll look at more of this in the next lecture. So what I'm going to do in the next lecture is the following. I'm going to look at the statistical mechanics of these semiconductors. I'm going to derive how the conductivity varies with temperature, how the mobility varies with temperature. So this is going to be my next lecture. And in the lecture that comes after that, I'm going to talk about some semiconductor devices. All right. And then I'll have two makeup lectures recorded, which will deal with looking at Brillouin zones in real crystal systems, 3D. And then I'll have one session on just a review problem on phonons in 2D. And I'm going to upload homework number 8 as well as the solution to homework number 7. Homework number 8, I think since it falls into the dead week, I will not grade it, but I will still expect you to complete it and send it to me if you want. So any questions about today's lecture? So today's lecture was just a curtain raiser on semiconductors, and I hope to take it further in our next lecture on Tuesday. So any questions?
सर हमारे पास जो सेमीकंडक्टर की टाइप है वो एक्सट्रिंसिक है या इंट्रिंसिक है, वो सिर्फ उसके जो बैंड है, जो नया बैंड इंट्रोड्यूस हुआ है उसकी लोकेशन पे डिपेंड करेगा, और वो डोपेंट पे डिपेंड करेगा कि कहाँ बनता है हमारा नया बैंड.
हाँ जी बिल्कुल. So if you have an extrinsic semiconductor, it can be of the N type or it could be of the P type. There's another kind of doping as well, which is called compensation doping, but we'll not cover that. Yes, so you're right. So it really depends upon the location of the chemical potential. In an intrinsic semiconductor, the chemical potential is in the middle of the band gap, almost in the middle of the band gap. At 0 Kelvin, it's right bang in the middle of the band gap. For an N-type semiconductor, it's closer to the conduction band, and for a P-type semiconductor, it's closer to the valence band. And this is the topic of my next lecture as well. So we look at the location of the chemical potential.
Okay sir, thank you.
So have you all submitted homework number 7?
सर वो तो काफ़ी देर पहले ड्यू था.
ठीक है, चलें, ठीक है जी, बहुत शुक्रिया, थैंक यू वेरी मच. इंशाल्लाह सी यू ऑन
ओके
ट्यूसडे.
सर, अल्लाह हाफिज़.
अल्लाह हाफिज.